Hi, and welcome to this presentation on different ways that you can measure efficiency against a given technology. So, efficiency measures. In any benchmarking problem, you kind of face two problems. The first is to estimate the technology to get an impression based on real data, what the technology looks like, maybe estimate a cost function. And the other one is to measure the performance of a given unit relative to that technology or that cost function. And although DEA kind of combines those two activities, namely the estimation activity or the measurement activity, one can look at the measurement issues in relation to technologies that are not estimated by DEA. And therefore, it's relevant to take just a look at different ways to measure efficiency if we already know the technology. We'll later then return to the question of how to actually get knowledge about the technology and how to estimate the technology. So this one focuses on the measurement problem. And the outline of the presentation is that I'll first discuss why are we interested in efficiency to begin with, and then I'll discuss how we can measure efficiency when we don't have any prices on for the outputs or for the inputs. And then I will discuss next how we can refine our measures if we do indeed have prices, input prices or output prices, or both input and output prices. And as the last set of measures, I'll discuss dynamic efficiency. How can we measure changes in efficiency over time? How does the frontier shift, and how does my position relative to the frontier shift? And then I'll conclude, and the appendix contains various less important additional material. So let's get started. And first, let's look at the relevance of efficiency. So the notion of efficiency is all over the place in economics. And one of the things we like to discuss in economics is how the market ensures efficiency. If you have perfect competition, you have these first and second welfare theorems saying that you will end up in a Pareto efficient allocation of resources, for example. That's the first one. And the other one says that any such can be supported by a price system. So efficiency is very important in economics. And what notion of efficiency is used in economics? Well, that's basically a 0-1 notion. Either you are efficient or you're not efficient. So let's start with that, and then later we'll discuss how to measure the degree of efficiency. So the notion that is typically used in economic textbooks is the notion of Pareto efficiency, or sometimes also called Koopman efficiency. I assume that X's here represent inputs and Y's represent outputs. So here I have a unit that have used X cap 2 superscript 2 inputs and Y superscript 2 outputs have been produced using those inputs. And I would say that such a production plan dominates another one with superscript 1, if and only if this one, the first one, the dominating one, uses at the most the same inputs and produces at least the same outputs, and is not exactly the same. So it means that at least one of the inputs must be smaller in X2 than it is in firm 2 than it is in firm 1, or at least one of the outputs must be larger than the output produced in firm number 1. So to illustrate this, you can just look at this picture down here. You can see that it's very hard to compare firm 3 and firm 2, because firm 3 is using less input and is also producing less outputs. But if you look at X2, it's spending more inputs, but it's also producing more outputs. So they don't really dominate each other. But if you look and compare firm 2 and firm 1, you can actually see that firm 2 dominates firm 1, because firm 1 is using more of the input X and is producing less of the output Y, than this firm up here is. So we can say that this one here is a dominated firm or production plan, and this one dominates this one up here. You can also say that you can now define the set. If you have a set of firms or production plans, you can find that subset which is efficient, and we call that the set of firms that cannot be dominated. Okay, that's the efficient subset of this T. So here I have a bunch of different production plans, the gray area, and I'm wondering which of those are efficient. I'm looking here at the output side of things, and I assume that all these firms are using the same inputs. And of course, if you take a point like this one here, where my red bullet is right now, that cannot be an efficient point, because I can find another one that are using the same inputs. All points here are using the same inputs. They're using the same inputs, but I could increase both of my outputs and still be inside the technology. So this is all the points inside here are not efficient. What about the boundary points? Well, this one, for example, is efficient because I cannot find any points that are producing more of one output at least, and possibly more of both output, but at least one output should be able to be expanded. I cannot expand the second output because then I move outside the technology. I also cannot expand the first output because then I'll move outside the technology. So all the points here are efficient. The same goes down here. But as soon as I start to curve inwards like here or like here, it's no longer an efficient point. So take this one, for example. Why is this not efficient? Well, I can find a point, for example, a point up here that are producing more Y2 and is producing the same level of Y1. I can also find a point out here actually that are producing more of both the Y1 and Y2 if I compare this point down, a point down here to a point up here. So that's the notion of efficiency, and that is basically what we would call like the Pareto efficient production plans. Okay. Now, why is this a relevant concept? Well, you have to go back to the basic idea of economics, that is that decision makers are rational. And what does it mean to be rational? Well, it means that you have some kind of a preference function, like the U, you get some value when you use X to produce Y. And you want to find the production plan that maximizes your utility. If you can find a reasonable utility function such that a production plan can be motivated as the solution to this basic decision problem, then you would say that this firm has acted rationally. Okay? And the reason why we like efficiency is because that is linked to this kind of rational behavior. It is a necessary condition for firms acting rational. It's not necessarily sufficient. It's a necessary condition, but it's not necessarily a sufficient one. So you can actually be efficient without really being rational. And sometimes in the benchmark literature, we also distinguish between efficiency, which basically means you have to be on the frontier, and effective means that you have to be at the right place on the frontier. If you go back here, you could say that if you have a preference function, maybe preference function will have an isoquant that moves like here. You know, maybe I can even draw that. I don't know if I can draw that. Can I do that? Well, I can probably do that. So I can do like here. So assume that you have a preference function that goes something like this. That means that this point down here will be the utility maximizing production plan. Okay, so that will be the effective production plan, because effectiveness in the benchmarking literature means that you maximize your utility. And you can see that you need to be on the frontier to maximize your utility, but it's not all points on the frontier that maximizes utility, because if you take a point like here, then you'll actually get a utility function that goes like here. So you get a lower indifference. You will be located at a lower indifference curve. Okay, so we go back to this one here. So efficiency is necessary for effectiveness, but it's not sufficient for effectiveness. How do I get this one moving again? Let me see if I can. Okay, here we go, I think. No. Just need to figure out how to get back to pause. So the fact that efficiency is necessary for effectiveness of a rational behavior, but is not sufficient, that's basically what is stated in this proposition here. It says that if you have a decision problem like up here, where you want to maximize utility, and where you assume that your utility is sort of natural in the sense that it is increasing in the outputs and decreasing in the inputs, which it's weakly increasing, which means this condition here, then we have that for any solution to the decision problem, then we can find another solution, possibly another solution that is efficient and that gives at least the same at least the same utility. So what does this really mean? Well, it means that it's enough to look among the efficient plans. You can say also that for any efficient plan, there exists a utility function such that it is the unique optimal solution. So the second part basically says that you cannot cut down the set of points, efficient points, any further unless you have a utility function. You know something more about your utility function. So it's sufficient to look at. So this is a little bit different from what I said up here, from this condition here. This one basically says that it is enough to consider the efficient plans, and you cannot upfront disregard any of the efficient plans unless you have more information about your preferences. And that's basically what I'm writing here. It's suffices to look among the efficient plans, and you cannot reduce the search any further without more specific information about preferences. Okay, so that's sort of the economic rationale for looking at Pareto efficiency or Koopman efficiency. Now let's try to measure and either you're efficient or you're not efficient in a Koopman sense or Pareto sense. But maybe you're very close to a point on the frontier, and you might therefore ask, could we get a more detailed measure of the degree of efficiency, a degree of inefficiency? And that's what this next section is all about. So the single most important notion of efficiency in the benchmarking literature is this notion by British statistician Farrell. And it's very simple. It's basically asking what is the largest proportional reduction of all inputs. So if that is, for example, 0.6, it means that you could take all the inputs and still be inside the technology. So basically it means you have a production plan, and now you can reduce all your inputs in that production plan to 60% of the old level. So basically you're saving 40% of all the inputs. And this reduced input bundle is still enough to produce the outputs. You could also ask on the output side, what for the fixed input, for given inputs, what's the largest proportional expansion of all the outputs that is feasible inside the technology? So if you get a score of 0.8, it means that you could have increased all of your outputs with 80% without needing more resources than you already have. So a large value of this output-based Farrell efficiency is the sign of a large inefficiency, and a small number of this input efficiency is indication of a lot of inefficiency. Okay, and if you want to translate these expressions here to math, you can look at this picture up here. So you have input 1, input 2. So if I have in this left panel here, I assume that outputs are fixed. And so I have a production plan here. I have the isoquant corresponding to the output of this firm I'm looking at, and it's located here. So you can see I have been using more inputs that is strictly necessary according to the input isoquant, the minimum input able to produce the output. And now if I want to do proportional reductions, it basically means that I'm moving this point towards the 0 point of the coordinate system here. So in this case, you can see if I stay here, I have to multiply. So the question is, what should I multiply on this x? If I multiply 1 to x, I stay at the point. If I multiply 0 on x, I end up down here. And if I multiply 0.9 on x, I move it down here, 0.8 and so on. And so that when you get down here, I've multiplied a factor of approximately 0.6 as down here. Likewise over here, if I multiply this number, this vector here, all the coordinates in that vector, I multiply with a scalar, which is larger than 1, then I'm being moved out according to this dashed line here. And I can continue to do so inside the technology until I reach this point here. Okay, and so this may be, I can multiply it with a factor 1.8, and that means that the Farrell output efficiency is 1.8. I could have produced 80% more of all my outputs without expanding the use of inputs. Technically, you just write it like here. Input efficiency is the smallest factor I can multiply on my input vector, such that this reduced input vector is still able to produce this output vector y. And it basically means that this input-output combination is inside the technology. This is what happens over here. And on the output side, I just want to maximize a factor f such that the input x and the output fy is still inside the technology, which is what happens over here. So very, very simple idea. And I spent a little bit of time explaining this, but the coming pictures I'll of course go through more speedy. So if you don't understand this, make sure stop and try to make sure that you can really translate these pictures into these formula and vice versa. The Farrell measure is very popular and it's probably used in 95% of all benchmarking study, or maybe even more. And what's the reason for that? Well, the reason is that it's really easy to interpret. It basically summarizes. There's so many things you could say about a firm like this one here. Okay, you could save a lot on output 2. You could also save, something on output 2. You could save something on input 1. You could save a lot on input 1, but a little bit on input 2. Then you end down here. So it's hard to describe the sort of the level of inefficiency. But if you want to sort of summarize it in just one number, then you say, okay, let's just do proportional reduction. Let's use the same reduction factor on all the inputs and stay inside the technology. So it's really easy to interpret. Summarizes these many dimensions in just one number. We also saw in the presentation on regulatory benchmarking and on the combination of agency theory and benchmarking techniques that this way of measuring actually makes a lot of sense, for example, in a downsizing context, when there's a lot of asymmetric information between the principal and the agent. If the principal have no clue about the relative importance of the input factor or the relative cost of the input factor, then the best he can do is actually to ask the agent to reduce proportionally. Because if he asks them to reduce more on input 1 than on input 2, so it doesn't move towards the 0 point, but he moves in a slightly different direction. So if he asks to reduce mostly on input 1, he'll just say that, okay, but that doesn't really reduce my my cost very much, because it's not really or my necessary effort, because it's not really this production factor that is so important. It's more the other production factor that is important. So we have these sort of strategic, you can always argue that the least reduced output, for example, is the most expensive output to produce. Those kind of sort of strategic discussions back and forth. Anyway, so there's a linkage to agency theory, but most importantly, for most benchmarking study, it's just easy to interpret the Farrell measure. The biggest problem with this measure is that it's not exactly measuring that you cannot, based on this measure, see whether a production plan is really Koopman efficiency or Pareto efficient. And that's what I'm trying to illustrate here. So assume that you have an observation here. I have a technology output isopoint that looks like this. What happens is that I get projected out here. Okay, so I can see that our present production plan is not efficient. But now what happened if I was starting out here, then I couldn't expand any further. So this one will get an output efficiency of 1. So it will look fully efficient from a Farrell point of view. But of course, it's not fully efficient from a Pareto point of view, because there I could actually have expanded output D and just kept my output C constant. So I could have moved from here in this direction here. So it leaves some slack. So some of those that get a Farrell efficiency score of 1, and therefore a degree of efficiency equal to 1, they are actually not Pareto efficient because of this slack problem. We call this difference here, we call this a slack. So that's the first drawback of the measure. And the second drawback of the measure is that if you now have, for example, 2 hospitals and they both have an efficiency of, let's say, 90%, but they have a very different composition of resources. So maybe one has 2 doctors for every nurse, and another one has 2 nurses for 1 doctor. Then you can say that, okay, you can save 10% of all your resources, but it's not the same to save. Can you really say that it's equally good to be able to save 10% of, let's say, 0.2 doctor and 0.1 nurse, or is it better to be able to produce to save 0.2 nurses or 0.1 doctor? Okay, so you're actually kind of comparing organizations that are doing very different things, but they might nevertheless get the same efficiency score. And it basically means that the interpretation of the Farrell measure, some could be tempted to argue that you will get the same score for firms that are very different because they have a different composition, for example, of nurses and doctors. Okay. Some literature on benchmarking will use something called a Shephard efficiency measure. And it's very easy to explain what a Shephard efficiency measure is, because it's always just the inverse of the Farrell efficiency measure. So instead of trying to multiply a factor on the inputs and to minimize that, you try to divide the input with a factor D and then to maximize that factor. So just look at this and you will see that it is actually just the inverse of the Farrell efficiency. And likewise on the output side. So before, a low value of the input efficiency was bad news because it indicated a lot of inefficiency. Now a large value of the Shephard input efficiency is bad news. And similarly, you have to reverse the conclusion when it comes to the output Farrell efficiency. So that's one idea. I want to introduce a few other ideas one can easily use. We'll stick for most of this presentation, we'll just stick to the Farrell efficiency. Now, what if you have several inputs and it's only some of them you can actually control? So there might be, for example, that you cannot easily lay off doctors, but you can maybe more easily lay off nurses. Okay, so if some of these inputs cannot be controlled, then it doesn't make much sense to say, yeah, but you can save 10% of the nurses, 10% of the doctors. You'll just come back and say, but I can't really save, I'm not allowed to change the number of doctors I have affiliated with my hospitals because of labor union laws or agreements or whatever, other kinds of sort of medical regulations. So in that case, you will just try to do the savings in the variables you can actually change. So we tend to distinguish between variable inputs or variable outputs. We also sometimes call them discretionary inputs or discretionary outputs, because it is at the discretion of the agent to choose that level. So you can distinguish between factors that you can actually vary and then factors that are fixed or non-discretionary, something that you cannot choose to change as a firm or as a hospital in our example with doctors and nurses. So if you have such a situation where some variables can be changed but others cannot, and you want to measure now input efficiency, then you just try to say what's the proportional reduction of all the inputs that's feasible, all the variable inputs that are feasible, when I have to end up with a production plan so that this reduced bundle of variable inputs and the fixed inputs, I haven't reduced that, and the variable outputs and the fixed output are still inside the technology. Okay, and you can do the same on the output side. So you only try to expand some of the outputs. If some of the other output, it doesn't make sense to change those. Okay, so if we were to, if I can just go back here. So if we were to do that, let's assume, for example, that input number one is a fixed input, it's a non-discretionary input. Then the only thing you want to do when you want to measure the efficiency of this guy is to move down here. You cannot change this one because I assume that it was fixed or non-discretionary. So you will measure efficiency by moving in this direction here. So in this case, input efficiency will be this level down here, the level I get down to here, divided by the level I have up here. So it'll be even more, for most technologies, it'll be more than the Farrell efficiency, because you only save in one dimension, or in this case in one dimension, but in a subset of the dimensions that is at stake. Okay, so that's this idea. There's another idea. I'll just mention a couple of slightly older ideas of extending this idea of Farrell, because we saw that Farrell is either reducing the inputs or it's expanding the outputs. And then some people were thinking that, okay, why don't we simultaneously reduce the inputs and expand the outputs? And one way to do that is to use a hyperbolic relationship, so that when you go up here, when you change this, then you also change the y with 1 divided by the x, basically. So it means that if this is my present observation, and when I want to calculate this hyperbolic efficiency, then it means I'm doing a projection of this point along this hyperbolic function here until I reach the technological frontier here. And then the level here, the relationship between this level and this level will be 1 divided by g. Okay, so that's another idea. It's not something that is being used a lot, but I think we actually have implemented it in our benchmarking package. The other, we noticed before that there's a difficulty with the Farrell efficiency, namely that it might leave slack on the table, so to speak. You might get an efficiency score of 1 and still there might be some slack. And there's been some different ways to suggestion for how to handle that. Färe-Lovell has proposed an alternative measure, which is this one here. And it might look slightly complicated, but it's actually not so complicated. Basically, what we try to say is we can reduce the first input with some factor, the next input with another factor, and the final input with another factor, these lambda 1 to lambda m. So we can use different reduction factors. And then what you try to do is you try to find such a movement towards the frontier such that the average reduction factor, so here I take the sum of the reduction factors and then I divide by the number of factors that are actually being reduced, that this average reduction factor is as small as possible. This factor that I multiply, the average factor that I multiply on the inputs is as small as possible. Okay, there's another proposal, is namely the Zieschang efficiency measure. And the idea of that is that first you project to the efficient frontier using the Farrell approach, like the proportional approach. And then after that, you use the projected point and evaluate its Färe-Lovell efficiency relative to the technology. So here you first get to the technology, and then you capture the slack by basically making this final movement from the proportional hit point to a point where there's no slack left. Okay, and it's easy to show that the Farrell efficiency is higher than the Zieschang efficiency, and the lowest efficiency is this Färe-Lovell efficiency, because there here you have some restrictions in how going from here to here you get rid of the slack. So that because Färe-Lovell is always going to be smaller than 1, so that explains the first one here. And the reason that Färe-Lovell is even smaller than this one here is that here you're kind of restricted in the movements you do. You moved along the parallel, or you make proportional reductions, and later you get rid of the slack. You can get to the same point using the Farrell, but using the Farrell you can get to other points also. So therefore you're going to get an even smaller number there. Okay. If you want to discuss these measures in a more abstract sense, there's also some axiomatic theory about that. So from a very abstract point of view, you can look at efficiency measure as basically a mapping of, let's say, inputs, an input vector, m-dimensional input vector, and a technology into the real numbers. So a way of measuring an efficiency is basically a way that once you have an input vector and once you have a technology, you can summarize the performance of that input vector in that technology into one single number. Okay. So we would like ideally that this idea that we come up with, it has certain properties. And I mentioned 5 properties down here. You can pause it and look at it, but let me just go through them fast. One is invariance to permutations and rescaling. So basically it means 2 things. It means it doesn't really matter the order in which we list the inputs, whether we take doctors, nurses, and capital, or we take capital, nurses, doctors. It doesn't matter which order we do it. It also doesn't matter how we scale them. It doesn't matter whether we measure capital in millions or in thousands, for example. So that's invariant to permutation and rescaling. Okay. Indication is the one that Farrell had problem with. It basically says that if you get an efficiency score of 1 if and only if you are Pareto efficient. Okay. And we know that that is not the case with Farrell because there was this potential slack problem. The third assumption is, or property, is that of homogeneity of degree 1. And basically what it means that it means that if you double your input consumption, then you become your efficiency level is halved. Or so it's basically if you multiply lambda on the input vector, then your efficiency score is lowered, and it's lowered by the factor lambda. Okay, this is supposed to be lambda to the power of -1. This one should have been in superscript. Monotonicity in inputs, it says that if you use strictly more of at least one input, then you should also get a lower efficiency score. Okay, that's also a problem for Farrell, as we already know, because you could have this again that you can maybe spend more of one input, but it doesn't necessarily mean that you can therefore reduce all the inputs. It just creates slag in one input. And then the final one is a sort of a technical mathematical one. It's continuity. It says that this function here is continuous in the lambda variable. So we don't want that you increase your input with 10% and then 11% and then 12% and sort of going in a sort of continuous movement and the input vector, then you see some huge jumps in the efficiency scores. Then the efficiency score should also gradually decline. Actually, it's declining when you increase your input. Okay, so these are natural properties, all of them you can argue. And now we can then discuss for these different measures, the Farrell efficiency measure, the Färe-Lovell efficiency measure, and the Zieschang efficiency measure, which of these properties they have. And they're all invariant to permutation and to rescaling, so that's all fine. Indication we knew is a problem with Farrell, that was the slag problem. It's not a problem with the other ones. Homogeneity, this one has, and Zieschang has, but actually Färe-Lovell doesn't have it. Monotonicity, we also noted just a split second ago that because the slag problem, it's not fulfilled by Farrell, but it is actually by Farrell, but it is by Färe-Lovell. And continuity, this one has more or less, and the other one, it does not have this continuity property when you look carefully at it. Okay, the final one I want to kind of notion I want to introduce is this idea of directional distance functions. Farrell moves in proportion, Farrell makes proportional reduction, so it moves toward the 0 point, but in principle you can move against any other point. Okay, you can say, for example, for me it's really important to get rid of some nurses. I would like to lay off several nurses every time I lay off a doctor. So if this one, X2 is the doctors and this is the nurses, then you would maybe want to move in this direction here. Okay, so every time I lay off, I need to lay off basically 4 nurses before I lay off one doctor. That could be one strategy. You could also turn it around and then be much more aggressive against the doctors, if this is a hospital example. But anyway, the idea is that you can, if you fix this direction, then you can measure the efficiency of any point by just looking at how many times can I move in this, what's the distance in this direction. Let's use this one, for example. What's the distance from here to the frontier? And then if you have another one, then you move in the same direction, mainly firing nurses, and you end up down here and so on. So that is directional distance functions, or it's also Lundberg introduced it, and he called it like the excess function. So what's the excess of resources you have? So here we use a measure E. So it's like more like an additive measure. So we say that what's the maximum I can factor, what's the maximum number of times I can subtract this direction on the input set from my input. And here I have just fixed output, so let's forget about this. So how many times can I reduce this, my input vector with this vector here? And if I can reduce it, so you can see, for example, here, I've calculated it. So you can reduce the income consumption in this direction 0.48 times. So you can take more or less half of this input vector and subtract from the present input level and still be inside the frontier. Okay, So, and then you could, so you'll get one measure if you use this direction. Here I use another direction. Jesus. Namely, I move in this direction here. And then you could say that, okay, for this, in this direction, I have a value of 0.38. And if I were to move in this direction there, I would get a value of 0.75, which is actually the same as the Farrell measure. But what is important to notice that this depends, you have to use this measure, you basically have to decide upfront or by some other means in which direction are you interested in moving. And it's also important to understand that this is like an additive measure. Farrell was like a multiplicative measure. You say, how much could I have reduced? So by which factor, what's the largest share of my input I could remove? Here we say, how many times could I move from the input set, from the input vector, this vector of inputs here. So it's like an additive measure rather than a multiplicative one. This way of thinking is actually precisely the way that we think in this interactive benchmarking that you might have tried and which was described in this presentation on the introduction to benchmarking. And there we allow for both movement, change, direction on the input side and the output side, like which was actually also the idea of the original Leuenberger one. And the way that we define those directions is by moving these bars around, okay? So if I move this up, it means that I would really like to go in this direction, and I would also like to go in this direction. So here, basically, I want to move in all inputs and output directions, except for this one. I'm slightly less interested in expanding this output. So here we have input 1, input 2, output 1, output 2. And what I'm saying is I would like to reduce my two inputs. I would also like to expand the second output, but the first output, I would like to expand it, but it's less important to expand that than it is to expand the other one here. So that's basically what I'm doing. And the way I set this basically determine these directions, x and dy. Okay, so that's about different ways that you can measure efficiency when you have a production plan, inputs used, output produced, and you have a technology. You don't need any prices to do any of these measures here, which is really one of the reasons these new techniques have become very popular, because in many cases, particularly in the public sector, you do not have prices. You do not have obvious ways to value the outputs, for example. So let's maybe ask if anyone has any questions here, but otherwise I will continue and I will move on to efficiency and prices. Actually, let's break this this video here, and then I will make another video where we look at efficiency measure with prices, like a second part of this presentation, and then I'll make a third one where we look at dynamic efficiency. So the videos do not become too long. So it's good to have a short break here. Okay.